Hello again, fellows. In this part, I'm going to present reservoir simulation models and field development strategy. During this lesson, we will define what we mean by a reservoir simulation model, consider its benefits, review the key uncertainties associated with reservoir simulation, and present the main issues in defining a field development strategy. At this stage, we will focus on the third part of the reservoir engineering scheme, which is the reservoir modeling. Let's begin with a basic definition of reservoir simulation. Reservoir simulation is the process of inferring the behavior of fluid flow in a petroleum reservoir system, and it's a powerful tool for guiding reservoir management decisions. The main objective of reservoir models are, in the appraisal phase, to identify uncertainties and define the needs of data. Then, in the field development phase, to identify production mechanisms, define the number, location, and type of wells, predict production profiles, and assess the risks associated to the project. From this, we can conclude that it's indeed a tool for decision making. Let's introduce now the data synthesis and integration in the reservoir modeling. In the construction of a reservoir model, the main input are the geological model, explained previously by Professor Anjardin, which represents the reservoir by a grid containing millions of blocks, each of them populated with properties such as porosity and permeability. The fluid, which is characterized to define the type of fluid and the phase diagram. The fluid flow behavior, which will define how easily 2 or 3 phases flow simultaneously in the porous media. The production data, which concern the reservoir pressure and fluid rates during the production phase, allowing the production mechanisms to be assessed. All these data are integrated in the reservoir model, which is more or less complex depending on the project objective. Once the data have been integrated, we can introduce the reservoir model. The complexity of questions and the data available will determine the sophistication of the models to be used. Here, we will only introduce 2 models. The tank model, which is a zero-dimensional model useful for initial reservoir estimation, and the upscale reservoir simulation model, which is a 3-dimensional model. Let's begin with the tank model, which is a very simple model where the reservoir is represented as a homogeneous volume with a unique porosity, pressure, etc. Here, the material balance equation is solved, and the main objectives are to check the data consistency, estimate the fluids in place, and predict production profiles. Then we have the upscale reservoir model, where the reservoir is represented by a grid in which the space is discretized in 3 dimensions. The geological grid is upscale to reduce the number of blocks in order to simplify the resolution. Let's call a generic block I, exchanging oil, gas, and water, with its neighboring blocks. Solving the material balance equations, we obtain the pressures and saturations for oil, gas, and water at each time step and for each block. The result will then be oil saturation and pressure distribution evolving with time. Let's see an example. Look at this segment with 1 injector well, I1, and 2 producers well, P1 and P2. Looking at the oil saturation distribution in one layer, we observe the waterfront advancing from the injector well to the producer wells. The flow shows a channel path that corresponds to a fluvial depositional environment. When we implement reservoir simulation modeling, we can simulate different well locations and perforations, production and injection rates, etc., which allow us to evaluate different strategies in order to optimize the reservoir performance. As seen until now, modeling and simulation imply data interpretation and assumptions. Therefore, it's necessary to consider the uncertainties, such as the fluid in place, the geological description, the presence of an active aquifer, the fluid and flow properties, and the rock properties distribution. These uncertainties represent the risk of the project and might be reduced by carrying out seismic surveys, drilling appraisal wells, conducting well tests, etc. Now that we understand how reservoir models are built and what we can obtain from them, we will be able to understand how useful they are to evaluate different strategies to develop an oil field. Looking at the life cycle of a hydrocarbon field, the development phase involves the choice of the initial development plan and the construction of the field's production facilities. Reservoir simulation models are used from the appraisal phase right up to the end of the production to define the field development strategy. Let's now focus on the field development plan. In order to set up a field development strategy, we must first describe the field and understand the field behavior. These points were covered in the two previous lessons. Secondly, several development strategies need to be formulated based on a series of reservoir simulation studies. The main objective being to determine the production profile, the number of wells, their location and type, and to estimate the impact of uncertainties. Finally, the management will make a decision based on the evaluation of production profiles, economic performance, and risk. The first step is the description and understanding of the field behavior, as we have just seen together. The second step in the field development plan involves the prediction of the production profile. A typical production profile includes a ramp-up phase related to the increased number of wells. This plateau rate is usually fixed as a percentage of the estimated ultimate reserves, and a decline phase due to pressure decrease and to an increase of water and gas production. This phase might be mitigated by water or gas injection or any improved oil recovery technique detailed later on. In order to predict the reservoir behavior, it's important to understand the production mechanisms in each phase of production. In the natural depletion phase, the production mechanisms present will be fluid expansion and pore compaction. Afterwards, an aquifer may be present or more or less active, giving some pressure support to the system. The pressure support can also be external and produced by water or gas injection. The reservoir engineer must then answer these different questions. What is the target for reservoir pressure? When will the injection start? Which fluid will be injected? Finally, in the decline phase, we can implement an improved oil recovery technique, enhance oil recovery, infill drilling, artificial lift, etc. At this stage, we are able to propose different configurations for wells, resulting in different production profiles. We begin calculating the number of wells by dividing the plateau rates to be produced by an average production rate per well. Knowing that this is a theoretical calculation, we will implement different number of wells in the simulation models, different locations and perforation levels. In this example, the minimum number of wells to achieve the production plateau is 3. As we increase the number of wells, the plateau lasts longer. The difference between drilling 4 or 6 wells is very small. We must look then at the economical performance in order to make a choice. Is the incremental oil revenue higher than the investment? Have we reached the optimum number of wells? Another important issue in the well definition is the type of well. The most common types are vertical wells, recommended in reservoirs with vertical compartments. deviated wells depending on the reservoir structure, and horizontal wells recommended in narrow layers, low permeability reservoirs, and compartmentalized reservoirs. As we have seen, the reservoir model provides predictions of reservoir behavior for a whole range of possible recovery schemes. After having evaluated several field development strategies with their own production profiles, different well systems, number, location, and type of wells and economic performance, the options are compared and presented to the management. The management's decision will be based upon the production profile, the economic performance, and the risk associated to uncertainties. That is it for me. I invite you now to practice your new acquired skills through the next minigame. Wishing you the best for the rest of this MOOC, it's my time to say farewell. Thank you very much all.